All right, let's go. Electricity and magnetism.
At Geico Auto Insurance, we handle your claim quickly, so you don't have to bum a ride to work.
Okay, so what causes magnetism? What makes certain materials magnetic? Iron is very easily magnetizable, so is steel. Copper, not so much. Gold, forget it. All right, so what makes a material magnetic? That's one of the questions.
Has ever visited. No one has ever seen this place. Yet what happens here affects every one of us, every day of our lives. It's 2,000 miles beneath our feet. The Earth's molten core. Here, a vast ocean of liquid iron generates an invisible force. The Earth's magnetic field. It's what makes our compasses point north, but it does a lot more. It helps to keep the Earth a living planet. Our neighbors, Venus and Mars, have only weak magnetic fields, which means they're unprotected from the deadly radiation sweeping through the solar system. The Earth, on the other hand, exists within a vast magnetic cocoon. A force field that for billions of years has sheltered us on our journey through space. But now, scientists have made a startling discovery. It seems there's a storm brewing deep within the Earth. A storm that is weakening our vital magnetic shield.
The Earth's magnetic field has been our protector for millennia, and now it appears it's about to go away.
The Earth's magnetic field is getting weaker rapidly.
We cannot guarantee that the magnetic field of the Earth is still going to be there 1,000 years from today. Is our invisible shield about to disappear?
The question is not if that's going to happen, it's when that's going to happen.
Could the Earth really lose its magnetic field? And what will happen if it does?
Okay, so a couple of questions here that we need to focus on. Number one, what's causing the Earth's magnetic field? How does the Earth's magnetic field protect us? How does it protect us from space radiation? And it's getting weaker, so who cares? Is this something to be concerned about? Okay, so I love the song about magnetism. It's about time because gravity has a song. So how does the Earth's magnetic field generate magnetism?
It was a secret government program known as Project Destiny.
We're building a weapon that could generate targeted seismic events.
Designed to use earthquakes to attack our enemies.
I'm getting a seismic reading.
It was a perfect, untraceable weapon.
Destiny is a go.
Until something went wrong.
That's an electrical superstorm popping up all over the world. I'll put this as simply as I can. Everybody on Earth is down to you.
The core of the Earth has stopped spinning. The spinning core protects us from cosmic radiation. Without it, radiation will create superstorms. Microwaves will literally cook our planet. How could this have happened?
It was Project Destiny. We killed the planet.
So, how do we fix it?
We can't. The core is the size of Mars. You're talking about jump-starting a planet.
What if we could?
We're here about your legendary ship.
What would it take to get it in 3 months? $50 billion. You take a check?
We need you to control the flow of information.
You want me to hack the planet? I'm gonna need Star Trek tapes and Hot Pockets.
You are good. Is there anything you can't do?
Not that I'm aware of.
You're trying to save the world. It's impossible. I came here to save my wife and children. I just hope I'm brave enough to say breathe.
I can't wait to get into an untested ship, go to the center of the Earth, and restart its core with 1,000 megatons of nuclear weapons. Then we outrun the biggest shockwave in history.
Hot damn.
San Francisco is in ruins.
The whole West Coast is out, and it's decaying faster than we thought.
2, 1.
We're going in.
Whoever goes into the core is not coming back.
We're losing oxygen!
We got a job to do. Let's do it.
Okay, so according to the documentary that you guys saw, the core generates the Earth's magnetic field, right? How? According to this movie, the spin of the core is what generates the Earth's magnetic field. The premise of the movie is straightforward. The core stops spinning, the magnetic field is gone, so why not get a bunch of people, send them to the core, and let them just jumpstart the core again. Evidently, the problem with the whole thing is when the Earth's magnetic field vanishes, we become rather susceptible to the radiation from space. In particular, the sort of radiation that they're afraid of is microwaves. So the question is this: Earth's magnetic field, does it really protect us from microwaves?
Could it be true? Could a small magnetic clasp be erasing bank details? How hard is it to wipe out a credit card anyway?
Is it hard or is it easy using magnets?
And the escape blasted off into extreme ride history, earning rays for its maximum velocity, towering ascent, and seemingly endless airtime.
Foreshadow the future of roller coasters, or at least the future of the high end of roller coasters, the very technology intense, extreme experience that a roller coaster can give its riders.
Okay, so how did the magnetic levitation work about the propulsion? Magnetic propulsion. Speaking of magnetic propulsions,
This could be a caterpillar.
Oh, what?
The caterpillar drive. Magneto-hydrodynamic propulsion. You follow? No. It's like a jet engine for the water. Goes in the front, gets squirted out the back. Only it's got no moving parts, so it's very, very quiet.
Like how quiet?
It's doubtful our son not even pick it up.
What happened?
Sonar contact, Captain. Fourth quarter. Close aboard. American, Los Angeles class.
American, Captain. Course 310.
Is the American turning to follow us? No, Captain.
American is continuing in his original course. He's continuing northwest.
He can't hear us.
okay, so at the time of the making of this movie, sort of technology that they're talking about was science fiction. Today it's a science fact. So they have this magnetic propulsion unit. They call it the MHD, magneto-hydrodynamic propulsion unit. When it kicks in, the submarine becomes sonar invisible. So how does it work? The details is top secret, but the physics are great enough, so we'll actually discuss it. So magnets will have two poles, south and north. Where do we get the naming convention from? Straightforward. Just get a magnet, suspended through a string right in the middle. Somehow magically it's going to line up itself in the direction of the Earth's magnetic field. And pointing towards the north becomes the north pole of a magnet. Pointing towards the south becomes the south pole of a magnet. All right, so the compass is a magnet on a pivot. All right, so and pointing towards the north, you can line it up. It becomes the north pole on a compass. The nice thing about the compass is by using it, you can actually trace or map the magnetic field of a magnet. Magnetic field lines will always start at the north pole of a magnet, and they will point towards the south pole. They will start at the north pole and point towards the south pole of a magnet. Earth's magnetic field usually points north, just like that. This implies that the invisible magnet within is oriented in this fashion. Notice that the north pole of the magnetic field is coincident with the south pole of our geography, in essence. Now, where does the magnetism come from? In an attempt to figure that out, you can take a magnet and start breaking it into smaller and smaller pieces, check to see how far you can go. Regardless of how small the pieces are, it's always going to be magnetized, which means that it's always going to be dipolar or bipolar. So it's always going to have a north and a south pole. So the question is, where do we get the magnetism from? So something about magnets, the like poles will repel, non-like poles attract. Hopefully this is something we already know. There's nothing new about it. So here's what the physicists were curious about. What would happen to the charges when placed inside a magnetic field? All right, so B represents the strength of the magnetic field. Why do we use B? I don't know. It's traditionally B is what we use. So it's pointing from left to right. Here's a static charge. It's now moving. And when you place a static charge inside a magnetic field, nothing happens to the magnetic field. So if it's stationary, it's not going to move. That's what it means. So what would happen if we have a charge and move it parallel to the magnetic field? Again, nothing happens. The charge is not going to speed up, not going to slow down. It's not going to change direction. So if that's the case, what would happen if we send the charge across the magnetic field? Well, when you send the charge across the magnetic field, something weird happens. The charge will become deflected, but not in the way you think. It's going to get deflected in a direction which is going to be 90 degrees states motion. Completely unexpected. If you want to know why, let me tell you the answer. No one knows. Okay, so no one knows the reason why. But this is what happens. This is a description of what we see. So when a charge goes across the magnetic field, it's going to become deflected by a force. It's going to be 90 degrees states motion. So static charges, the stationary charges, will not experience a force. If the charge is moving parallel to the magnetic field, nothing happens. If a charge is moving across the magnetic field, it's going to experience a force. It's going to be 90 degrees states motion. Now, the direction of this force is determined by something called the right-hand rule. By the way, believe it or not, the right-hand rule does not work with your left hand. So in case there are some test questions that you will have to answer, you just remember to use your right hand. The way it goes is the following. So here's the direction that the charge is moving. That's the velocity vector. Line up your thumb along the direction of the velocity vector. Fingers lined up along the direction of the magnetic field. The force is going to be in the direction that your palm opens up. Okay, so this is known as the right-hand rule. There are two of them, so I'm going to give you the first one first. I will call it the right-hand rule number one. Direction of the magnetic field. The charged particle is moving in this direction, so you line up your thumb in this direction, the fingers line up along the direction of the magnetic field, and your palm is going to open in the upward direction. All right, so this is the direction of the deflection. This is the angle between the force and the velocity vector. Regardless, the force is always going to be 90 degrees to the motion of the particle or the charge. Okay, two-dimensionally, we will do a two-dimensional representation of three-dimensional space. If the arrow is coming out of a page, this is the symbol we will use. If the arrow is pointing into the page, this is the symbol that we will get to use. Magnetic field is pointing into the page in all of these cases. All right, so there, even in space, this represents a uniform magnetic field region. All right, so I get a positive charge moving in the downward direction, just like that. All right, so now this charge is going to experience a force. You can figure that out. So your thumb, line up your thumb in this direction, fingers pointing into the page. So which means that the force is going to be pointing to the right. So it's going to experience a force to the right. So which means that the charge is going to get deflected, just like that. Now the charge is moving to the right. Thumb in this direction, fingers into the page. So the force is going to be in the opposite direction. Charge is going to get deflected. At some point, it's going to be right here. It's going in the opposite direction. Thumb is in the opposite direction, fingers into the page. So the force is going to be to the right. And then the charge is going to get deflected. It's going to be here, right here. All right. Now it's going to experience the force. It's moving to the right. So thumb is going to be to the right. Fingers into the page once again, and boom, it's going to experience the force in the downward direction. Notice that regards to the motion, the force is always 90 degrees to the motion of the particle. It's causing a deflection, and deflection creates the circular motion. All right, so what that means is the charge going across the magnetic field is going to wrap itself around the magnetic field. So that's what happens. All right, so hence the reason why the magnetic field protects us, only protects us from charged particles coming from space, not the electromagnetic waves, guys. That's complete nonsense. It doesn't protect you from heat. It doesn't protect you from light. It does not protect you from radio waves. It does not protect you from microwaves. The Earth's magnetic field is there to protect us from incoming charged particles from space, stars, the sun, or whatever. Okay, so that movie completely missed that. In the movie Hunt for Red October, you got the propulsion unit that you're looking at. You should recognize the shape. Looks like a jet engine, meaning that when you force the water into a small opening, it's going to speed up. So the question is, how do you force the water into a small opening? At the end, straightforward. Notice that you have a very strong magnetic field in the opposite direction, and then one region is positive charge, the other region is negative charge. You get the charges to move in this direction real fast inside salt water, highly conductive. So the charge is moving in this direction using the right-hand rule will experience a magnetic force in this direction. So that magnetic force points in the direction of the nozzle, the opening of the nozzle. So it's going to force the water into a small opening. As a result, it's going to speed up. What that means is there's a force acting on the seawater, causing an acceleration. And so the action force is acting on the seawater. The reaction force is going to act on the propulsion unit. As a result, the vessel is going to accelerate. That's how it is done. All right, so magnetic levitation.
The ride's propulsion system is a simple yet complicated mechanism. A series of electromagnets, called stators, line the horizontal portion of the track. As the magnets beneath the car pass over a stator, it is energized, first to attract and then to repel the vehicle.
All right, so the magnetic propulsion works straightforward. Light poles will repel, non-light poles attract, right? Under the train, they got the permanent magnets. On the tracks, they have magnets that they can polarize that well. Okay, so depending upon where these magnets are right under the train, they're able to change the polarity of the magnets on the tracks as well. So how do they do that? They're able to do that because of something that this guy discovered. His name is Ørsted. I want you to remember his name. This guy's no Einstein. It's an important name. It's important, maybe not to you, but it's a big deal because, number one, this guy's Danish. And if you're Danish, that doesn't mean that you're pastry, which means that you're from Denmark. And this guy is the reason why we were able to have this little conversation that we're having right now, because I'm in Chicago, you guys are near Houston, and we're having this conversation because this guy discovered something. All right, discovered something in 1820, 1819. All right, so it's roughly about 200 years ago. And this guy is a big deal in Denmark because you will see his picture on their currency. It's that big. Accidental discovery. Giving a presentation, physics presentation, like he's teaching, and then he's got his students, and then he lined up the students, and he's got a simple battery, and then he's running a current through the battery, and then the wire would heat up. It would stop the current. The students would just touch the wire and then get this warm and fuzzy feeling, and then that's it. So that was the extent of the physics lectures 200 years ago. Touch the wire, get that little bit of a warm and fuzzy feeling, and then move on. And then so that, listen to the guy. talk. Anyway, so he was doing this experiment because he keeps repeating it. And all of a sudden, there's a compass on the table. As soon as there's current in the wire, you'll see a deflection in the compass, and he's going, "Oh, this is weird." And all of a sudden, he discovers that the current is what's causing the magnet.
Hans Christian Ørsted discovered that electric currents produce magnetic forces, and that those forces always make magnets point perpendicular to the direction of the current.
So evidently, what generates magnetism is the current. That's it. So the current is going up. Boom, there's a magnetic field around the current wire. So what generates magnetism is the electricity. Electricity is what generates magnetism. Electrical current is what generates magnetism. Now, what we'll do is we'll introduce a second right-hand rule. It goes like this. All right, so you line up your thumb in the direction of the current, and your fingers will curl in the direction of the magnetic field. We know the magnetic field goes this way because by using a compass, you can actually map it. So the current goes up, magnetic field wraps itself around the current. And Ørsted is the guy who discovered it. So current is coming out of the page, it's going into, no, the magnetic field is coming out of the page, it's going into the page. The current is in the opposite direction. So the current is what causes the magnetic field. Line up your thumb in the direction of the current, your fingers will curl in the direction of the magnetic field. The year is roughly about 1820. So that's 200 years ago. All right, so using the right-hand rule, your thumb is going to be pointing out of the page. If that's the case, the fingers will curl in this direction. So if the current is coming out of the page, the magnetic field goes this way. If the current is going into the page, the magnetic field is going to go in the opposite direction. I drew, okay, so I drew that wrong, but that's fine. If you have a loop, wire loop, just like that, if the current is going this way, the magnetic field is going to wrap itself around in this fashion. If you have multiple loops, which is called a coil, if the current is moving in this direction, notice that the magnetic field is going to be stronger, pointing in that direction. If you place an iron core in the middle, iron is very easily magnetizable, so the top is going to be the north pole, the bottom is going to be the south pole. And if you reverse the direction of the current, the polarity of the iron is going to get polarized. It's going to change now. North becomes south, the south becomes north. Guys, these are known as electromagnets. You created yourself an electromagnet. All right, so the electromagnets, you got an iron core, and you just magnetize it, in essence. Stronger the current is, the stronger the magnetic field, so that allows you to be able to pick things up. All right, so these are the electromagnets on the tracks. The only thing you have to do is just change the polarity.
The system, you're turning it this way with the track.
To watch some.
Could it be true? Could a small...
All right, so the myth busted by using an electromagnet.
Nothing's going to happen. It's good. Now, wave this card like half a centimeter above the magnet. Let's see what that did. Hey, we got a read error. Read error. We got a read error.
Swiping the card has proved the key. By moving it through the field, the tiny magnetic particles in the strip are dragged out of alignment.
1,000 Gauss.
Number 4 is totally screwed. Number 4 is bad. I would say that we can call 1,000 Gauss the point at which the cards regularly start to fail.
What that means is, but it's not that easy to wipe out these credit cards using magnets.
Look, this nail is not a magnet.
No kidding, it's a nail.
Right, it won't pick up these metal paper clips, see?
Right, it's a nail.
But if I run the nail over this really strong magnet several times, the atoms inside the nail will begin to sort of line up in one direction.
And what does that mean?
Well, it means the nail can become a magnet, see?
Okay, so the
Look, this nail...
iron is very easily magnetizable, so what's the reason?
A circular loop of electric current also creates a magnetic field of this form. And so does every proton, every neutron, and every electron in the universe.
All right, so the reason why
A circular loop.
iron is very easily magnetizable is because of the simple reason that the atoms are magnetic. They're small magnets. Okay. Atoms are small magnets. The reason why they're small magnets is because the electron is moving like this. Single electron moving like that creates a magnetic field because it's the motion of the charge creates a microscopic current, and the current is what generates magnetism. As a result, the atoms become magnetic. Notice that the overall magnetism is pointing in that direction. So the atoms are small magnets. All right, so most of us are not magnetic because the atoms are pointing in random directions, so the overall magnetism is canceled out. But if you can get all the atoms to point in the same direction, then it would become magnetized. Iron is kind of weird because it's got these small regions which are known as domains, within which the atoms are already pointing in the same direction. So if you can get all the atoms to point in exactly the same direction by using an external magnet, the iron becomes magnetized.
Can you tell us what makes iron different from other metals?
Well, for one thing, iron has the ability to become magnetized.
Could you explain?
Sure. In a piece of iron, like in any metal, the atoms face in different sort of random directions.
You mean like this way and that?
Yes, so to speak.
Objection, I'm bored.
Hang in there, Mr. Savage. Continue, Dr. Fullergast.
Well, if the atoms in iron can be organized somehow to face mostly in the same direction, that iron becomes magnetized. It would send out an invisible field of magnetism, a magnetic field, all around it.
That's exactly right.
Okay, just as the atoms in a bar of iron can be organized, lined up in one direction, they can also be disorganized. Stenographer Fred, would you kindly smash the nail with the hammer, please?
I don't think I could smash it kindly.
Right, well then just smash it hard.
Okay. Hi-ya.
All right, Fred, now that should do it.
No more smashing?
Now that its atoms have become disorganized, the nail is no longer a magnet. See, it won't pick up a paperclip.
Okay, so you can disorganize stuff by heating it.
One thing you may not know is
disorganize the orientation of atoms by heating it.
something that is magnetic can have its magnetism destroyed just by heating it. For example, this is an iron wire, and you can match this ball magnet. I'm going to destroy the magnetism of that iron wire by heat. We just do that. Now, as it warms up, you'll see that the wire starts to sag, but I'll have to get it almost red hot before it will fall off the magnet. I'll have to put a little more current in still. Now watch, and there it and fell off the wire. Now, of course, that I've disconnected the current, it's cooling down from the magnet again, like that. So magnetism can be destroyed by heating, and it's restored.
Okay, so let's talk about the Earth's magnetic field. All right, so here's the last topic. Last semester.
About how the core generates the magnet.
Yep. All right.
The close relationship of magnetism to electric currents create magnetic fields.
Now, there's no electric current going through the coil to start with. Well, the iron filings just go down like pepper in a pan, but if I turn on the electric current, then you can see by the current in this electric coil. So it's what we think gives rise to the magnetic field.
Okay, so let's talk about the Earth's magnetic field. One theory is the Earth's surface is slightly negatively charged, right? And then you know that the Earth is spinning on its axis. The motion of the charges is what generates current, so this is known as a surface current. If the surface current is in this direction, the Earth's magnetic field would be pointing in towards the south. The Earth's magnetic field points towards the north, so the surface currents, the theory does not explain the source of the Earth's magnetic field. The second theory is the core theory. Earth is spinning on its axis in this direction, so which means that the core is spinning in the same direction. And the core is charged, obviously, which means that they will generate a current in this direction. But then again, if the current is in this direction, then the magnetic field still will be pointing in the wrong direction. Only way the magnetic field is going to point in the right direction is if the core is spinning in the opposite direction of the spin of the Earth. Now, the core cannot spin in the opposite direction of the spin of the Earth. Okay, the core is under a tremendous amount of stress and tension. There's no way it can spin in the opposite direction of the spin of the Earth. So the spin of the core theory does not make sense either. So what that means is we don't really know where the Earth's magnetic field is coming from. Okay, so we are thinking that there's some conduction currents at the bottom. Somehow, it's not that the core is spinning, and within the core itself, there are just currents, and then the currents are in a direction, which is generating the Earth's magnetic field. Okay, that's it. That's the most modern theory that we can come up with.
The Earth's magnetic field we know to be caused by the flow of large-scale electric currents deep inside the Earth. There are other components of the field, but the main field, the dipolar component, is associated with these currents. We don't know exactly how the magnetic field is produced. We don't have an accepted model in detail for the production mechanism.
We still don't. I mean, this thing is 20 years old. We do have some theories. We have a supercomputer generated model that kind of agrees with what I just said. It's not that the core is spinning. You got the charges flowing this way and that way because it's molten metal, and it's flowing in the right direction in a sense to generate the Earth's magnetic field.